There's the question where can be formed the zeolite. It is metazeolite structure. As you can see, there is possibility to incorporate the metal pieces in isolated power, is more interesting. The isolated extra power piece and extra power metal. The objective of this work is to incorporate the metal ion in the proper position as isolated single star material. To reach this objective, two-step post-synthesis method and control of the preparation conditions within the metal precursor concentration is very important. Advantage of such operation is to restrict oxidation of transition metal in the zeolite as here metal structure. In the first, so first now we say about the stability of the zeolite as so this two-step process is composed of two steps. In the first step, there is removal of aluminum by asymmetric and formation of vacancy site OH group. This OH then in the second step, we contact this zeolite with ammonium metabolite solution. And in this condition, there is possibility to incorporate vanadium in the vacancy site by reaction of this precursor with OH group. So in this case, it should be the vanadium should be incorporated in the structure of the zeolite in the power position. So to continue that work, so we see the next slide. Not good. Okay. Excuse me. So, incorporation of vanadium ion into vacancy site at pH 2.5 is realized with small concentration of the ammonium metabolite solution in this condition, in pH 2.5 and small concentration, in the solution, we have only mononuclear vanadium species. So you can see that from the region of predominance of vanadium species, there in the another pH, there is a bigger complex situation, because in this condition we form different kinds of polynuclear vanadium species. In this vanadium species is very difficult to incorporate. So we see this after. So in the first, by infrared spectroscopy, we can see that in the first step, we have alumina beta zeolite with ALOH group. This group is presented in the infrared spectroscopy by the band at 3609. When we remove aluminum from the zeolite, we remove by treatment with nitric acid, we obtain vacancy site with OH group. This vacancy site is confirmed by infrared spectroscopy by the broadband at 3520. So then when we contact this vacancy site with the VO2 plus, so there is direction between this OH and VO2 plus, and mononuclear vanadium species incorporated in the Framwell position, and we form tetrahedral vanadium species, isolated tetrahedral vanadium species. Then by vanadium mass NMR, we confirm that when we have in the solution VO2 plus, this is VO2 plus band, and you contact this solution with SE beta, we observe that this band is disappeared, is decreasing in intensity. So this means that VO2 plus is incorporated in the SE beta, and we form vanadium SE beta zeolite. So in this is confirmed also by appearance of the band at minus 620. This band is characteristic for vanadium tetrahedral species. When we do the mass NMR, vanadium mass NMR, we can distinguish also in the spectra two kinds of vanadium tetrahedral species. This one is second one. So this means that there in the zeolite we have two kinds of vanadium tetrahedral species. By vanadium mass NMR, we can also observe that when the content of the vanadium is increased, so we form not only mononuclear vanadium species, but also tetrahedral and octahedral vanadium species, which is represented here. So by UV visible spectroscopy, we can also distinguish in the zeolite the presence of vanadium tetrahedral species, which is characterized by these two bands. But first one is related with oxygen tetrahedral vanadium charge transfer transition involving bridging VOSE, bridging VOSE, and the second one is related with the presence of oxygen tetrahedral vanadium charge transfer transition involving the of oxygen. So we can see also that when the content of vanadium is increasing in the sample, so we can observe that not only tetrahedral species is observed, but also hydrogonal species. This result confirms the same result obtained with vanadium mass element. Now, when we change the pH and concentration of the ammonium metabolite, we can observe by the region of Coriolis of banana species that when we, for example, were in the pH 6, so we have conditioned several types of banana species, mononuclear and polynuclear banana species. So we check what happened when we were in condition. From 2.5 to pH 6, and in this condition, when the pH we compare the result of human spectroscopy by prepared pH 2.5 to pH 6. So we can observe the difference between preparation at pH 2.5 and pH 6. And in this condition, we observe very big amount of hydrogonal species, because in this condition, in the solution we have polynuclear banana species. By this, we can conclude that the separation at pH 2.5 is better than the separation in pH 6. Because in this condition, at pH 6, we obtain fully resolved band at 3624 is related with the presence of vanadium beta species. Then we observe also influence of pH on the incorporation of vanadium species using silicon mass NMR. In this condition, we observe that there is big difference in preparation in pH 2.5, because in this condition, when we prepare it in pH 2.5, when we incorporate vanadium in the beta zeolite, we observe consumption of this band related with the presence of this kind of OH. And when we have only 0.7% of vanadium, there is already consumption of this band. And in contrast, in the case of preparation in pH 6, so we can observe that this band is not consumed completely. It's only partially consumed spectra. So now by EPR spectroscopy, we can observe big difference between preparation in pH 2.5. In this case, the preparation in pH 2.5. So we, in the case of calcined zeolite, vanadium is in 5 degrees of oxidation. So we not observe EPR signal related with the presence of vanadium 4, because this vanadium 4 is only present when we do ODH test. In this condition, there's a reduction of vanadium 5 to vanadium 4, and we observe the signal of signal EPR. By simulation, we can distinguish that in this condition, we have a ratio tetrahedral to octahedral species 10. So this means that it's practically only tetrahedral vanadium species present in the zeolite. Now, when we change the pH of preparation, pH 6, so we can see also that in this condition, Also, in the case of calcined zeolite, vanadium is in 5 oxidation state, and after oxidation degradation of propan test, we can reduce vanadium 4 to vanadium 4, and vanadium gives the signal. The signal is characteristic for tetrahedral or octahedral species. In this case, ratio to tetrahedral to octahedral species is about 0.5. This means that the small amounts of tetrahedral species in the zeolite prepared at pH 6. It means that vanadium is incorporated in the extra Fraunhofer position. It's not good for a reaction. Now, in this slide, I can show you result of oxidative degradation of propan, and we can see that when we do this reaction on vanadium Sc-beta zeolite prepared at pH 2.5, in this case, we have propan rate production 10 times higher than in the case of preparation pH 6. It means that tetrahedral vanadium species present in this case are much more active than octahedral vanadium species present in the case of preparation at pH 6. So all total frequency for this reaction is 10 times higher in the case of preparation at pH 0.5 than in the case of preparation of vanadium Sc-beta zeolite and pH 6. So we can see in this condition that there is advantage of preparation of the catalyst at pH 2.5. So in conclusion of this part of the work, we can tell that Fraunhofer and extra Fraunhofer addition of vanadium was controlled by the speciation of the vanadium species in the aqueous ammonium metabolite solution by changing of the pH and concentration of the precursor. At pH 2.5, we can see that predominant is mononuclear vanadium VO2 plus species, and this species is much more active in the oxidative degradation of propan than the polynuclear vanadium species mainly formed in the at pH 6. Now we can show that in this case there is this species, mononuclear vanadium species, incorporated in the Fraunhofer position is active site of propan degradation to propan, but not VO2 polynuclear vanadium species. Now I can show you also that NO conversion in selective reduction of NO with ammonia on vanadium Sc-beta catalyst prepared at pH 2.5 and pH 6. So we can see there's a big advantage of preparation the catalyst at pH 2.5 because this NO conversion for this catalyst is much more higher than in the case of preparation pH 6. So also in this reaction, N2O can be formed. There is not good products of this reaction. So the high production of this NO2 plus on catalyst with 7.5 weight % of vanadium, very big amounts of this N2O is formed because in this case we have mainly pseudotetrahedral vanadium species. In contrast, in the case of preparation pH 2.5, amounts of N2O is smaller. much more than in the case of catalysis with the high amounts of polynuclear species. Now I can show you a second application. There is preparation of tantalum beta zeolite by the same two-step synthesis method. In this case, we remove aluminum as in the for vanadium beta zeolite. We create vanadite site, and then we contact this vanadium OH group with tantalum precursor, organic tantalum precursor. In the second step, we incorporate tantalum in the Frammer position. We can check this after, but this catalysis with tantalum will be interesting in production of 1,3-butadiene from bioethanol acid aldehyde mixture. So we will see this after. So in the so we can see that formation of 1,3-butadiene from bioethanol is formed in the cascade reaction up to 1,3-butadiene. So for this we should have several kinds of species, active species in the zeolite with tantalum. So we confirm by XRD and infrared spectroscopy, then incorporation of tantalum in the SC-beta zeolite take place because we observe change of the position of the main diffractogram peak from this position to this and this when we incorporate tantalum. So this shows us that tantalum is incorporated in the zeolite because the size of unit cell is increased in this condition. Here, by infrared spectroscopy, we observe also that by incorporation of tantalum in the SC-beta zeolite, we observe change of the main peak at 955 to 965. This change is related with incorporation of tantalum in the Frammer of SC-beta zeolite. This shift is related with this. Now, by infrared spectroscopy, we can see that in the case of aluminum beta zeolite, we have several bands. When we remove aluminum, so we create vacancy site and isolated OH group. So in this case, we form OH group, hydrogen bonded OH group. And when we contact SC-beta zeolite with this OH group, this group is disappeared. This is related with direction between OH group present in vacancy site with tantalum precursor. In this case, this band disappeared. A new band disappeared. This band is related with the presence of tantalum 5 OH group formed in the SC-beta zeolite. Then by silicon mass NMR and proton mass NMR, we can show that when we incorporate in the SC-beta zeolite tantalum, this band, which is related with the presence of hydrogen bonded OH, is disappeared. And this means that reaction between OH group present in vacancy site and precursor take place. This is confirmed also by proton mass NMR. In this case, we have a characteristic band related with the presence of hydrogen bonded OH group. And also when we introduce tantalum, this band disappeared. It means that reaction take place between OH group and tantalum precursor. all these results show that tantalum is incorporated in the SC beta zeolite. Here we show infrared spectroscopy by adsorption of pyridine. So we can see that in this case, we have no pyridinium ion bands. That means that there is no bronze acid site in this zeolite. In contrast, there is Lewis acid sites because this band is related for this and this also. In this case, we form Lewis acid sites in the zeolite. But also by adsorption of pyrrole and by adsorption of deuterated chloroform, we can distinguish that in this zeolite with tantalum, there is several kinds of species. In the case of this band, this is related with the presence of acidic sites, and sugar in this case is related with the presence of basic sites. Here we can see that there is different kinds of basic sites in the zeolite with tantalum. So we think that these different kinds of active sites can be active in the reaction of formation of 1,3-butadiene. So here we can see the reaction, the result of the reaction, the conversion, total conversion, and of ethanol and acidic mixture. In this case, we form butadiene, and we can see that the selectivity to butadiene is relatively high in this condition. So we form above 90% of selectivity to 1,3-butadiene involve temperature on the zeolite with 1% of tantalum. It means that incorporation of tantalum in the zeolite give us to obtain good catalyst for production of 1,3-butadiene. So also butadiene selectivity and butadiene yield over tantalum 1 SC beta as a function of time of stream is very stable. So we can see that this catalyst is very stable because selectivity to butadiene and butadiene yield is for a long time on stream very similar. So there is no deactivation in this condition, and this is very good catalyst for this reaction. In conclusion, we can tell that tantalum SC beta zeolite with mononuclear tantalum 5 species can be used as efficient catalyst for the conversion of bioethanol and acetaldehyde mixture into 1,3-butadiene. So we can see that by this reaction, we can form butadiene with very high selectivity. And we can tell that two-step post-synthesis method used for tantalum incorporation into vacant site of beta zeolite have allowed preparing highly selective catalyst for conversion of ethanol and aldehyde mixture into 1,3-butadiene. So tantalum SC beta possess both acidic and basic sites, which allow to obtain 1,3-butadiene in the cascade reaction thanks of this. Thank you very much for very nice for you for a nice